Hey guys, welcome back. Today we're going to start chapter 7, which is on exponential and logarithmic functions. So we talked about inverse functions before break. Exponential and logarithmic are kind of like inverse functions. Well, I mean, they are. So we're going to learn a whole lot of new things with exponents, and then we're also going to do a lot with logarithms. It's going to be really great. So, be prepared, strap in, we're back at it. Alright, so for objectives, we're going to be answering the question, what trends do you see when graphing exponential models? And for objectives, we're going to model exponential growth and decay by graphing. Well, that's a little redundant. So by graphing. And then we're going to use the understanding of exponential growth and decay to solve applied problems. So I'm going to give you some problems where we're going to use these equations. Okay, so for our vocab, an exponential function is a function with the general form y equals a times b to the x power, where a and b cannot be 0, and b can also not equal 1. For exponential growth, as the value of x increases, the value of y increases. I mean, that makes sense. When one goes up, the other one goes up, things get bigger. And b is called your growth factor, because b is your value that's being, the exponent is being applied to. So if it's positive, it's going to grow. For exponential decay, as the value of x increases, the value of y decreases. So this is called our decay factor, because as one's getting bigger, the other one's getting smaller. And then we're also going to learn a new thing. An asymptote is a line that a graph approaches as x or y increases in absolute value. So an asymptote is just a line that your graph gets infinitely closer to, but never actually touches. Okay, so for exponential functions, here's our standard form, y equals a b to the x. So if a is greater than 0 and b is greater than 1, then the function is exponential growth. So if b is greater than 1, it's a positive number, things are going up, that's growth. If a is greater than 0 and b is between 0 and 1, that means it's some kind of fraction that's not a whole number. This is exponential decay. So between 0 and 1, it's decay. In either case, the y-intercept is 0a. That's where it crosses the y-axis. The domain is all real numbers. So every number that you put in for x has to be a real number. We can't put in imaginary numbers. The asymptote is y equals 0, and the range is y is greater than 0. So these are general rules for all exponential functions. So I want you to tell me, just by looking at these, whether or not they're exponential growth or exponential decay. Y equals 12 times 0.95 to the x. Well, if we look at our standard form is y equals a b to the x. So whatever our value is that's being raised to the exponent, that's going to tell us whether it's growth or decay. So what's being raised to the exponent? 0.95. Is that greater than 1, or is it between 0 and 1? It's between 0 and 1, so this is exponential decay. And your y-intercept is 0.12. What about this one? Y equals 0.25 times 2 to the x power. So we have to ask ourselves, what's being raised to the exponent power? 2 is. 2 is greater than 1, so it's exponential growth. And then our intercept is 0.25, or 1/4. Okay, you can model exponential growth or decay with this function. A of t equals a times 1 plus your rate raised to the power of t. So this is when we're talking about time. So after t periods, so whether it's minutes, seconds, hours, years, depending on what your information is, a is your initial amount. So a lot of times these are used with cells, like cells are growing at a constant rate, or due to medicine, cells are dying at a constant rate, or cancerous cells or whatever. So that's our initial amount. And r is the rate, and we always write the rate as a decimal. Alright, so let's say you invested $1,000 in a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? So we're going to use that equation, a of t equals a times 1 plus r raised to the t power. Um, Sorry, I didn't want to sneeze on you. So first we need to determine if an exponential function is a reasonable model. So does it make sense to use an exponential function in this case? Well, is the money going to grow at a constant rate if you have a 5% interest for at a certain amount of time and you only put a certain amount of money in? Yes, it makes sense to use an exponential model. So we're going to do that. Okay, so we need to define our variables. So A is our initial amount. So what was your initial amount that you invested? Well, that's the $1,000. Okay, what was your rate? Well, you have a 5% annual interest rate. But how do we write rate? We always want to write rate as a decimal, not a percentage. So if you remember to write as a decimal, we take and move decimal 2 places to the left. So it's 0.05 is our rate. And then what's our T, our time? We're looking at sixth grade is when you invested it, and it's 6 years later. So you're now graduating from high school. So that's 6 years. So we're talking about years as our time. So if we plug this into our model, so we want to know after 6 years, so A of 6 equals 1,000 times 1 plus 0.05 to the 6th power. So what we want to do first is follow order operations. We add 1 plus 0.05, raise that to the 6th power, because we always do things in parentheses. Then we do exponents, and then we multiply. So multiply that times 1,000, and you should get $1,340.10. So how much money did you make in 6 years with a 5% interest rate on that account? You only made $340.10. So 5%'s not that great. Okay, here we have endangered species. So there's a table that shows the population of the Iberian lynx in 2003 and 2004. Alright, so here's our table. If this trend continues and the population is decreasing exponentially, so you see in 1 year, and they went from 150 to 120. So if it decreases exponentially, how many Iberian lynx will there be in the year 2014? So we're looking 10 years in the future if this trend continues. Okay, so does it make sense to use an exponential model in this situation? I would say yes. So we need to define our variables. What's our initial amount? So we're looking at years since 2003. Why is the population? We want to know how many there are. We need to determine what our rate is. What was our rate of decrease? So what we want to do is we take y2 minus y1 and divide it by y1. So what's that difference? So 120 minus 150 and then divide that by 120. What was our rate of decrease? If you put that in, you get negative 0.2. Does it make sense that it's a negative number? I would say yes. Okay, so we found what our rate is. Now to determine how many there will be in the year 2014, we want to have our initial population as from 2003, 150, with our rate of decrease at 0.2, and then how many years is it from 2003 to 2014? That's 11 years. So we're going to go ahead and... Oh, I'm sorry. I forgot we're putting into standard form. Okay, so to find our B, my apologies. So to find our B, we have to take our rate, and B is 1 minus the rate, 0.2. So B is 0.8. So put that into y equals AB to the x. There we go. That makes way more sense. Okay, so 150 equals A times 0.8 to the 0 power. So A is 150. So here is our function. Y equals 150, our starting amount, times our rate, our B, which is 1 minus our rate, because it's a rate of decrease, 0.8 to the x power. So now we can say in 2014, starting with 2003, with our 11 years, plug that all in, and we get that if this trend continues, there will only be 13 Iberian lynx left. Those poor Iberian lynxes, they're so cute. Have you ever seen one? I feel like I should put a picture in. Give me 2 seconds. And here you go. What a little cute little baby Iberian lynx. Isn't he adorable? And there we go, we're done. What I would like you to do is I want you to go ahead and, we didn't do any graphing. So I'm going to have you graph. Just because graphing is so important, we need to learn how to do this. So using your y equals a b to the x power, I want you to graph y equals 2 times 4 to the x power and y equals -1 times 1/2 to the x power. And I want you to go over these with your partner tomorrow. So what you're going to have to do, you're going to have to make XY table charts. That should be a Y, not another looking X thing. Okay, so this is what I want you to do with your partner for your lesson check, is I want you to graph both of these. You should have 2 graphs tomorrow to go over these, and then I should have some time while the other class is reviewing their midterm to go over these with you so I can show you. Like, it's really important that you learn how to graph. There's so much to graphing, and I know a lot of you don't like it, but the more you practice it, the more you get comfortable with it, the more confident you're going to be, and you're going to do great. Alright, so don't forget to do the lesson check, do these 2 graphs, and then I want you to, come to class, be prepared to do stuff and learn, and it's going to be great. Okay, anyway, talk to you later. Bye.